considerable attention has been devoted to the characterization of superconducting coil, which is crucial for the design of electric power applications such as motor and generators, because it allows to determine the critical operating current and the electromagnetic properties, and also to consider the influence of the magnetic field on the distribution of the current densities. This is generally achieved by combining measurement and modeling. The experimental measurement concerns generally global quantities such as the current and the voltage across the superconductor, while the modeling concerns the local effects. So in DC characterization of HTS coils, the current density is generally considered uniformly distributed in the coil cross-section. However, this is not realistic due to the dependence of the magnetic field on the critical current density. So in this work, a more realistic modeling approach is proposed with non-uniform current density and electric field distribution inside the coil cross-section, considering A of G characteristic and JC of B dependency. Now I will present the DC modeling approach. The modeled system consists of a circular pancake coil. Here the cross-section geometry of the coil, while each tape is discretized into elementary section, delta S, in the radial and axial direction. The modeling approach is based on numerical integration of the Biot and Savart equation to calculate the magnetic vector potential and the radial and axial component of the magnetic field, combining with a strategy that considers the non-uniform distribution of J. The coil is fed by a DC current IA, and using the current divider, we can express the current in each elementary section as follows, while Ri is the electric resistance of the elementary circuit of section delta S, and R is the resistance of the tape of section ST excluding delta S. Using the power law, we can finally obtain the expression of the current in each elementary section located at radial coordinate Ri and depending on the applied current. Here, a correction factor is added to ensure the conservation of the current inside the tape. The strategy considering the influence of the JC of B dependency on the distribution of the current density is given by this flow chart. After the initialization of the parameters, we consider a uniform distribution of the current inside the tape, and we evaluate the component of the magnetic field, and then we re-evaluate the critical current JC of B using these equations, and the critical current gives the new distribution of the current inside the elementary section delta S using the developed expression. And this equation is solved iteratively until convergence using the stopping criterion based on the minimization of the power dissipated in the coil, which is given in this equation. The modeling approach is applied to the characterization of two types of HTS coils: inductive coils for applications such as motors, and non-inductive coils for applications such as superconducting power filters and fault current limiter. I will start by the non-inductive coils. So the modeling approach is applied to a circular pancake non-inductive coil wound with D-Bisco, dynamically innovative Bisco tape. Figure A shows the schematic view of the coil, and here the photograph of the coil. The specifications are given in this table. So being non-inductive, the magnetic field around the coil is weak, close to the cell field of the tape, and below the value considered in the experimental data giving JC of B dependency. So to overcome this problem, a characterization method is proposed at the coil scale, and I will present it in the next one. So the modeling approach is combined with a least square method using the experimental voltage current curve to identify the parameters of Kim's law, giving JC of B dependency, and the exponent n of the power law. So in this table, I show the result of the identified parameter for a uniform and non-uniform current distribution in the coil cross-section. As expected, the zero field critical current is significantly affected by the non-uniformity of the current distribution. This results from the power minimization criterion. Here, the distribution of the radial component of the magnetic field and the current density over the coil for an applied current. So we can see that the magnetic field in the central region is low, and the current is maximum in the center. But at the edges of the tape, the situation is reversed. So we have maximum field and minimum current. This figure shows the evolution of the power dissipated in the coil during the iterative procedure. At this point, we have the maximum power when we consider the uniform distribution of the current inside the tape. After the third iteration, while we have considered the non-uniformity of the distribution of J, we have the power tends to decrease and become stable after 10 iteration. Now, by zooming in the inner tape, we can see that the radial component of the magnetic field affects more significantly the distribution of the current for an applied current. In this, this results show the normalized current density in the inner tape for different applied current, and we can see that the normalized current density distribution is quite homogeneous inside the tape, with small increase in the when going to the inner side of the tape, while decreasing the radial coordinate. So the modeling approach is also applied to the characterization of an inductive coils, circular pancake coil wound with Debisco tape, and here the specification of the coil. By performing AC characterization, we found that the inductance varies significantly with the current. So for more accurate design of HTS coil, it's essential to consider this evolution of inductance with the transport current. The inductance values are calculated using the magnetic energy, either by integrating the product A times J over the HTS volume, or by integrating the product B of H over the truncated space. Here the result, the experimental and numerical results of the inductance with respect to the current. We can see that at low current, we have similar results, but when increasing the current, the experimental results show an increase of 3% of the inductance, but the simulation predicts only 0.7% increase of the inductance, even when we take into consideration the elliptical cross-section of the HTS coil. So the distribution of the radial component of the magnetic field and the current density, while considering the elliptical cross-section of the HTS part in each tape of the coil, we have here the result. We can see that the central region subjected to lower field carried larger current, and at the edges we have maximum field, minimum current for an applied current of 40 amps, for example. I will finish by the conclusions and perspective. So in this work, a fast and realistic DC modeling approach is proposed, and it is suitable for the characterization of HTS coils. The influence of the magnetic field on the distribution of the current density is studied. Presenting local effects, considering the non-uniformity of the current density, is crucial for HTS system sizing, and the model is fast enough for the design and optimization of large-scale HTS coil. The future work will be AC modeling to better identify the variation of the inductance with the transport current in the same condition the measurement were done, and to evaluate the AC losses and the proximity of the active materials. Thank you for your attention.
How did you introduce non-uniformity into the material? Is it predetermined, or is it an arbitrary uniformity, or is it obtained by the experimental measurement, or is it a systematic non-uniformity?
It's not obtained from measurement. since we can have because we have visco tape, so we don't know the filament of HTS inside the matrix, Silver's matrix, because it's truncated tape. So we consider a non-uniformity inside the coil each tape. So it's not from the measurement one. It's only simulation.
Do you want to mention that you didn't know the non-uniformity? You do not apply a non-uniformity. You estimated the non-uniformity, right? Did you apply a non-uniformity to your tape?
Exactly.
Or you calculate a non-uniformity of the tape?
We developed the expression of the current in each elementary section, since the tape is discretized into different elementary sections, rectangular one, and we calculate the current in each little section, so we can have the distribution of the current inside the tape, and which is non-uniform.
Thank you. Other.
Thank you. Just a comment. The non-uniform distribution arises naturally from the minimization of the power in the tape cross-section. So it's calculation, and the system tries to evolve to this distribution by minimizing the power inside the section of the tape. May you show the second slide of and because I think that the question was not clear for Sara. Yeah, because she thought that it was obviously clear, but here, yeah.
We developed this equation, and by minimizing the power dissipated in the coil each time, each iteration, we have finally the new distribution of the current inside
How would you do it
if
it was uniform? You get what I mean? How would you get it if it was uniform?
Well, actually, in the initial condition, the current density is uniform inside the tape, and we calculate the magnetic field and the JC of B, and we calculate the current density in each elementary section. So we have a non-uniform distribution, but this is not the last distribution that we wanted. So we minimize the power dissipated each time. So we have finally the new distribution of the current, and this one that we use it to our work.
Okay. Thank you very much.
Thank you. There is one question of Professor Izumi. He asked if you will complete your study on DBSCO. Why you choose 1G tape? In this case, I think 150 amp is a good choice.
So we studied in first generation visco tape. I think we can apply the model also for a second generation. I don't know if we will have accurate results, but since it's a modeling approach, so we can apply it to the second generation also. We choose a 150. It's just an example. We can apply it to different current, and we still under critical. So we have the critical current is 170. So we choose an applied current which is lower.
Okay. There is still.
I have one comment. Can I talk?
Yeah. Who is talking, please?
Yeah.
Professor Izumi. Okay.
Maybe you can you know in case of the 1G, the DIV there is an anisotropy. So for practical reason, not so. Maybe it depends on how to use, but what is your target for your application?
What is
Final destination in your.
I'm sorry, I didn't get the question. What is
the final destination for your application target? Is it just a coil or motor, generator, or?
What is the final application is looking for?
So for the non-inductive coil, it's a stabilizer, superconducting power filter, and for inductive coils, it's for application for motors. So the modeling approach is applied to both type of HGS coils.
One question was related to the anisotropy. Do you think your numerical model can fit with the anisotropy? They already fit with? Yeah.
Yes, I think, yes, we can.
Yeah, we have to do something to overcome this kind of problem. Thank you very much.
Thank
You're
you.
welcome.
There remains one question in the assembly. We have still some couple of minutes. So here.
I think we have a question.
It's okay. Thank you. So let's thank the speaker again, and from the organizer, since we have some time, I will deliver the certificate to